So this is note 7.5, graphing exponential growth functions. We're actually going to do decay functions as well, but today and tomorrow we're just going to be doing growth functions. So from left to right we will be growing. Before we start the actual section, let's just start with a hypothetical situation. So listen up. Let's say that a mysterious man comes up to you on the last day of school and says, I need you to wash cars every single day for 30 days straight during the summer. I'll pay you good money. You ask him how much. He responds, whatever you want. You say $1 million. He stops and thinks and says, sure, I can give you the million, but how about instead of $1 million, I give you a penny right now. And on the first day of work, I'll double it and give you 2 cents. And on the second day of work, I'll double it and give you 4 cents. And after that, I'll double it and give you 8 cents. And so on for 30 days straight.
More than 10 million.
Now, what I want you to do, is to quietly talk to a partner and see if you would prefer the million up front or the pennies doubling day after day. Only 30 days. Only 30 days. I'm going to keep recording here. Since you guys have already talked, how many of you, raise your hand, would pick the $1 million up front? Okay, so all of you would be instant millionaires, right? Yeah. Now everybody else, wait a minute, how many people would pick the penny and then doubling and then doubling? Okay, not that many of us. But if you were to pick the penny, doubling, check it out. They give you 1 cent on that day 0, and then you start working, they give you 2 cents for that whole day's worth of work. And then day 2, it's 4 cents. Day 3, 8 cents. Day 4, 16. Day 5, 32. Day 6, 64. You keep multiplying. After 1 week, on the 7th day, after working all day washing cars, he only gives you $1.28. That sounds pretty miserable, right? But then we keep going. Multiply it by 2, 256. Double it, $5.12. Double it, $10.24. Double it, 20. Double it, 40. Double it, 81. Double it, 163. Double it, 327. Double it, and you keep going. Now, by the time... That's still not a million. That's still not a million. But look, by the time you get to the 27th day, on just on the 27th day, you get paid over $1 million. 28th day, 2 million, 29, 5 million. Okay, time out. Okay, don't get too excited. This is not really happening. Nobody's going to pay you. It's just hypothetical situation. Okay, so not only, I lost $9 million if I picked the $1 million. That's not true, because you actually have to add the 10,700,000 with the 5 million plus the 2 million. So you really lost like about $20 million by picking the $1 million. Anyway, why am I starting exponential growth with this hypothetical situation that's not real, obviously? Why am I doing that? Because exponential growth functions, at a certain part of the graph, it looks like it's not growing much. 2 cents, 4 cents, 8 cents, 16 cents. But the further you go on in time, it grows crazy at the end, right? That's what exponential growth functions do. It doesn't look like they're going to grow that fast, but at the end of it all, they grow really fast. Let's take a look at the notes on exponential growth functions. So by the end of this period, you will be able to graph exponential growth functions and also be able to state the domain, the range, the y-intercept, and the asymptote of any exponential growth function. Okay, so let's first start with vocabulary. We have our important vocabulary here. Domain, we already know, are the x values. Range are the y values. Parent graph we'll get into later. Translation is the way you move the parent graph. You can move it left, right, up, or down. We'll get to that later. Y-intercept is where it crosses the y-axis. How do you find that? You set x equal to 0, plug in 0 for x, and then you solve for y. That'll tell you where it crosses the y-axis. And the word asymptote is something very important, something new. Asymptote, if you read it a certain way, it would be asymptote, but that's not the way to read it. You say asymptote, okay? Now, what is asymptote? An asymptote is the line that your graph will infinitely approach but never actually touch in the case of exponential growth functions. And it will be y equals k. We don't even know what k is yet, but this is the form that we want the exponential growth functions to look like. y equals, a is just a number, b is the base, x is the exponent of x minus h up here in the exponent position, and then plus k at the very end. Now, in Algebra 2, we're going to be using all of this. In Algebra 1, we're not really going to be using the h. It'll just be a, b to the x, nothing else up here, and then just plus k or maybe minus k. Now, I know it all sounds confusing right now, but it'll become a lot easier once we actually see some graphs. So let's start with the easiest type of graph, which is this one, y equals 2 to the x. This is the one that we actually did on the pennies doubling, right? On day 0, you had 1 penny. On day 1, you had 2 to the 1 power, which is 2. On day 2, you had 2 to the 2nd power, which is 4. So this is a really easy graph to do. Let's all start by copying down this xy table, and by using consecutive integer inputs like -3, -2, -1, 0, 1, 2, 3. I want them in perfect order like this. If you put like 1, 3, 7, 2, it's going to be all messed up, and we're not going to be able to take shortcuts. If we use the numbers, the input numbers that are perfectly in order, we're going to be able to identify some patterns and be able to skip a lot of math. So copy that down, please. And let's start by plugging in the x values, which are the inputs. Which is the easiest input to plug in? -3, 0, right? If I were to plug in 0 right there, what is 2 to the 0 power? If I went 2 to the 0 power is 1, remember? Yeah. Anything to the 0 power is 1. So ladies and gentlemen, that is a coordinate 0, 1. Let's go to the xy plane and let's put 0, 1, put that dot right there. Let's go to the next one. If I were to plug in a 1, what do I get out? 2. If I plug in a 1 right there, 2 to the 1 is 2. So my output is a 2. So let's go to the coordinate 1 on the x, 2 on the y. So here's the origin. 1 on the x, 2 on the y. You'd be up there. So let's put a dot right there. And let's look at the next coordinate. If I were to plug in a 2, what do I get out? 4, right? If I go 2 squared, that's 4. So let's plug in a, or we plugged in a 2, we got out a 4. Let's graph that. 2 on the x, 4 on the y would be up here. Let's put a dot right there. And how about 3? If I plug in 3, what do I get out? 8. Oh, yeah, 3. Right? Because if I go 2 to the 3rd, that's really 2 times 2, which is 4 times 2, which is 8. So let's do the coordinate 3, 8. 3, 1, 2, 3, and 8 all the way up here. 3, 8. Okay, now what if I were to go backwards? Now, if I were to plug in -1, if I were to plug in -1 right in there, it's going to be 2 to the -1 power. So think about that, 2 to the -1 power. Do you guys remember negative exponents? We had to get them and move them to the other side of the fraction, and they become positive. So I'd have to get this whole term, move it down. I'd have nothing left up on top, and I'd have 2 to the 1 on the bottom, which actually becomes 1/2, right? So for the input -1, you get the output 1/2. Are you with me? What if I were to plug in a -2 right there? I'd have 2 to the -2. I mean, you could technically do this on the calculator. 2 to the -2 power. And what would you get as an output? 1/4. That's right. So let me put a 1/4 right here. And you know what? I might as well say this now, guys. Listen up. Whenever we're dealing with exponential growth functions, you're going to have some type of base right here. Yay? If your base is bigger than 1, which it is, that's how it's going to grow. It's called the growth factor. Okay, the growth factor. Now, when you have consecutive integer inputs, when they're in order, and you plug in 0, we plugged in 0, we got out a 1, you could actually get the rest of these numbers without doing any more complicated math. If you have the 1 right here, and you know that your growth factor is 2, then how would you get from 1 to 2? You multiply by 2. 1 times 2 is 2. And then you multiply by 2, you get 4. And you multiply by 2, and you get 8. Does that make sense? Now, if this would have been a 3, then it would have been 1. That would be a 3. And then that would be a 9. Because 1 times 3 is 3. 3 times 3 is 9. And then 27. Are you with me? But it's not a 3. It's a 2. So the growth factor is 2. So I could do all the math that we just did. Or I could say, oh, the growth factor is 2. So from 1 times 2, I get 2. 2 times 2, I get 4. 4 times 2, I get 8. And backwards, how would I get from 8 to 4? Divide by 2, right? Divide by 2, you get 2. Divide by 2, you get 1. 1 divided by 2 is what? 1/2 or 0.5. And then 1/2 divided by 2 is 1/4. And what's 1/4 divided by 2? 1/8. Are you with me? Yeah, 1/64, and then 1 over 128, and then 1 over 256, and it keeps getting smaller and smaller. Yeah. Now, let's actually graph the 1 1/2, the -2 1/4, and the -3 1/8. So let me actually zoom in to show you. So -1, let me put a dot at the origin here. The dot at the origin, that's the origin, but -1 is right here, and then halfway up would be right there. Okay? So you guys are going to have to get pretty close to your paper. So that's halfway up. And then the next coordinate was -2 and 1/4. So -2 and 1/4, that would be half of the half. Does that make sense? So I'd have to put the dot right there. And then the next one would be -3 and 1/8, which is even smaller. It's half of that half of that half. So that would be right here. And at some point, we can't draw it any more closer. We're going to draw it like if it's actually touching. But we know that it doesn't really touch. It just infinitely approaches. Does that kind of make sense? Yes. So this is your exponential growth function. Let me graph it. I'm going to graph it in red. Now at this point, I'm just going to draw it. It looks like it's actually on the x-axis, but it never actually touches the x-axis. It just infinitely approaches. Okay? So from left to right, like right here, from here to here, it doesn't seem like it's growing a lot, kind of like at the beginning of that word problem we had. But then all of a sudden it skyrockets. The last couple of days on that 30-day period, you ended up with millions of dollars. So that's how exponential growth functions actually work. It looks like from left to right, it's not growing that much, and then all of a sudden, grows a lot. Now, we do need to understand this interesting concept of going backwards. If I'm going backwards, see, this y level is 8, this y level is 4, this y level is 2, this y level is 1, and then half of that's 1/2, and then half of that's 1/4, half of that's 1/8, half of that's 1/16, 1 over 32, 1 over 64, 1 over 128, 1 over 256. It keeps getting smaller and smaller and smaller, but will it ever actually get to 0? No. Never. Okay? Now that's hard to believe, but let me give you a real live example right here. Okay, so here's a demonstration of me infinitely approaching something but never actually touching. Okay, I'm going to take 4 steps towards the wall over there. Okay, hold that, and record my feet. All right. So here we go. 4 steps that way. Feet. 1, 2, 3, 4. Okay, and then I'm going to take half of that, which is what? 2 steps. 1, 2, and then half of that. 1 step, and then half of that. That's half a step, and then half of the half, and then half of the half, and then half of the half, and then half of the half. Next, I'm just doing this, kind of like dancing cumbia. But my point is, I will never actually get to the wall. Does that make sense? Yes. Never actually get to the wall. Can you explain why? Because you're only traveling half of the distance that you were traveling the previous time, so you never actually get there. And you could even, I mean, that's visually, you could do it on a calculator. You could get like, you could take the number 8 divided by 2 on a calculator. What's it going to say? 4. Divided by 2, it's going to be 2. Divided by 2, it's going to be 1. Divided by 2, it's going to be half. Divided by half, it's going to be 0.25. Divided by 2, it's going to be 0.125. And it'll keep getting closer and closer to 0, but it'll never actually get to 0. Make sense? Yes. So that is a description of how the graph infinitely approaches. So I hope that we understand that as we go to the left, like right here, the levels 8, levels 4, levels 2, levels 1, this is half, this is 1/4, this is 1/8, 1/16, 132, 1 over 64, and it gets closer and closer to 0, but it'll never actually touch. Okay, so that's the exponential growth function right there, y equals 2 to the x. Now we need to understand a couple of things about that exponential growth function 2 to the x. Let's talk about the domain values. The domain values are the x values, right? And the range values are the y values. So when we talk about domain, we're going to be talking about the values on x. So does this red graph, does it go to the left on the negatives on the x forever? Yes. Right? The arrow means that it continues forever. Now, does it go to the right forever? Does it have positive x values?
No.
Sure it does. Look, oh, right here is the x value of 0. Here's the x value of 1. It exists right there. Here's the x value of 2. It exists right there. Here's the x value of 3. It exists right there. Does it exist at x equals 10? Yeah. Even though it doesn't look like it on the graph, it looks like it goes straight up, but it'll never go straight up. It'll actually, what I'm saying is, could you plug in 10 right here? Yeah, 2 to the 10th. That'll be a huge number off the screen, but nevertheless, it exists. So when I'm talking about domain, I'm talking about all the x values of this graph. So we would say x equals, it goes to the left forever, it goes to the right forever, so we say x equals all real numbers. And that's a symbol for all real numbers. Are you guys following along? Yeah. Okay, now the range are your y values. So let's think about the y values. Over here, the positive y values, down here, the negative y values. Does it go up forever? Yes. Does it go down forever? Yes. Over here, there's negatives? No. So where is this graph at in terms of y?
In the middle.
It goes up forever. So it starts here. In terms of an inequality, you would say y is greater than 0. Y is greater than 0. Because every single y value on this exponential growth function is above 0 on the y. You guys, does that make sense to you guys? So the asymptote was the line that our graph infinitely approaches but never touches. So we're talking about this green line right here, which is the x-axis. But we're going to call it the asymptote. We're going to say y equals 0. So our graph going to the left will infinitely approach that green line, the asymptote y equals 0, but it'll never actually touch it. It'll just infinitely approach it. Now the y-intercept, where does this red line or this red curve cross the y-axis? Right here. What is that location? 0, 1. So for the y-intercept, we put 0, 1. And that's really pretty much all that we could say about this exponential growth function. So let's practice by doing 2 more of these. See, down here, I have y equals negative 2 to the x and y equals 1/2 2 to the x. I'm just throwing some different things. I want to put a negative in front so you could visually see how that affects this original graph of y equals 2 to the x. By putting a negative in front of the 2, something crazy is going to happen with this graph. By putting a 1/2 in front of the 2, it's going to change it a little. So we're going to graph those so you could see how it changes. So let's go to the left part of this graph and do a xy table with consecutive integer inputs from -3 to +3. And what value is the easiest to plug in out of all these numbers?
0.
0. If you plug in a 0, 2 to the 0 is what? 1, but there's a negative in front of it, so it's actually -1. When you plug in a 0, you get out a -1. Now we can, let's actually graph that first coordinate, 0, -1. That's down here. 0 on the x, -1 on the y. Now we can continue to do this math. Plug in a 1, do the math. Plug in a 2, do the math. Plug in a -1, do the math. But the easier thing to do is to recognize that this has the growth factor of what? 2. The base is 2, so it's going to grow by 2. Only when the inputs are in order, the outputs will grow by 2. Okay? So this next value right here, if I take this -1 and multiply it by 2, what do I get? -2. If I multiply it by 2, what do I get? -4. Multiply it by 2, -8. If I were to do the next one, 4, I would get -16, but that would be off the graph, so I'm not going to use it anymore. Does that make sense? Now, that's only because the base is 2. If the base would have been 3, which on the back side we do have 3, then you're going to be multiplying 1 times 3 and you get 3. And then times 3 and you get 9. And then times 3 and you get 27. But right here, it's growing by 2. The growth factor is 2. So if it's growing by 2, 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8. Going backwards would be dividing by 2. So -8 divided by 2 is -4, divided by 2 is -2, divided by 2 is -1, divided by 2 is what? What's -1 divided by 2? -1/2. Come on, guys, dividing by 2. And then -1/2 divided by 2? -1/4. And then divided by 2?
-1/8.
-1/8. So you see the pattern, guys. Only because you have consecutive integer inputs, only because the inputs are in order, you could actually do these patterns of doubling and then dividing by 2. Not only that, you can see the pattern right here, 2, 4, 8. It's the same pattern in the denominator, 2, 4, 8. Are you with me? So let's graph all of these. Let's go to the next coordinate, 1, negative 2. 1 on the x, negative 2 on the y. It's right there. And let's go to 2, negative 4. That would be down here. Let's go to 3, negative 8. That would be down here. And I'm not going to go for 4, 16 because that's off the graph. Let me go into the negative direction, negative 1 and half. So if I did go, here's my origin, negative 1 on the x, and then halfway down, I'd be only halfway down. Let's put a dot right there, halfway. And then half of the half would be 1/4, and then 1/8, and then 1/16. Now, we can't really continue to draw infinite closer. It's going to look like it actually touches. So I'm going to draw it like if it's actually on it. So this is my exponential growth function. So by me putting a negative sign in front of the base and the exponent, what happened to the graph that was growing up? It now what? Slowly goes down, right? It's still a growth function, but it's not growing in a positive direction, it's growing in a negative direction. Now some of us might be thinking, wait, how could it grow in a negative direction? It's this simple. If you have a credit card and you don't owe any money on it, your balance will be 0. But then if you start using it and using it and using it and never paying off anything, it's going to grow negatively. It'll grow in debt, right? So it's still a growth function, just in a negative direction. So what would the domain of this red line be? What's the domain? X equals all real numbers. Once again, does the graph go to the left forever? Yes. Does it go to the right forever? Yes. Even though it's going down here, it still exists over here. Like if I plugged in a 10, I'd just end up with a really negative number somewhere way down, even below this. Does that make sense? Yeah. So the domain is all real numbers. What about the range in terms of y? Is the graph anywhere in the positives on the y? Is it anywhere up here? Remember, here's y is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is it anywhere in the positives? No. It's all down here below what value? It's below this value, below 0. That's the asymptote, right? So y has to be below 0. You can't even say below or equal to because it never actually touches 0. It's always below 0. It'll infinitely approach 0 but never actually touch 0. Do we get it? And of course the asymptote would be y equals 0, that green line, y equals 0. Now let's try the other one. Let's do an xy plane for the other one. I mean xy table for the other one. And let's do consecutive integer inputs, -3, -2, -1, 0, 1, 2, 3. Now if I were to plug in the number 0, the easiest input up here, what's 2 to the 0? Or right here actually, 2 to the 0.
1.
And what's 1 times half?
0.5.
1/2 or 0.5. Now I could, if I want to, plug in the number 1, work out the math, multiply by half and get another output. And then I could plug in the number 2. 2 to squared is 4, half of 4 is 2, and you get a 2 right here. So you could do all the math. But if you know how your base works, and you know that this 2 is really the growth factor, that means that it's going to grow by 2. So you're going to be multiplying by 2 as you go. So from here to here, what's half times 2? What's 1/2 times 2? That is 1. And then what's 1 times 2? 2. What's 2 times 2? 4. And then 4 times 2? 8, if you had the input 4. Does that make sense? And going in the opposite direction, you'd have the 1/2, and then what would be the next one? 1 what? 1/4, and then 1/8, and then 1/16. So let's graph this blue coordinates, 0, half. 0 and half would be right there. And then 1, 1 would be right here. And 2, 2 would be right there. And then 3, 4, it would be right there. And then 4, 8, it would be right there. And if you went 5, 16, you'd be off the graph. But if you're going in the negative direction, -1, 1/4, that would be right there, half of the half. And then 1/8, and then 1/16. And it infinitely approaches the x-axis. So that blue line, or that blue curve, represents this top exponential growth function. So again, the domain to any exponential growth or decay function is going to be all real numbers. Okay? So the domain for the blue one is going to be x equals all real numbers. That's true for any exponential growth or decay function. Okay. Now the range is going to be what? Y is what on that blue graph? Is it above a certain value or below a certain value? The blue one. It's above what?
A certain value.
Above 0. So y is greater than 0 is the range on that one. So we're actually going to stop this video right here, and we're not going to deal with h or k. Well, actually just k. We're not going to deal with the k shift yet. I would like you to maybe flip the paper over and try number 1, because number 1 is exactly like the ones we've just done. It just has a different base. It has the base of 3. So you could try that one, and we'll pick up on the second video explaining the other more complicated ones. So we will pick up the next video right here where we have functions like y equals a times b to the x minus h plus k. And we're going to actually be able to graph this one on the next video.